Hi guys, in this video I cover AVL trees. AVL stands for the first letters of Adelson, Velsky and Landis, who invented the AVL tree. An AVL tree is a binary search tree which satisfies two conditions. The first condition ensures that the difference between the height of the left subtree of a node and the height of a right subtree of that node is no more than 1. The second condition ensures that the left and right subtrees of any node are AVL trees themselves. In other words, these two conditions ensure that for any given node in an AVL tree, the height of the left subtree and the height of its right subtree differ by no more than 1. These conditions ensure that the AVL tree remains balanced by keeping leaves at a similar depth and ensuring that the tree does not morph into a linked list. Now, these two conditions are guaranteed by a balance factor, which is computed by taking the height of the left subtree and subtracting the height of the right subtree from it. A valid balance factor must be -1, 0, or 1. Any balance factor outside of the valid range is invalid. Adding or removing nodes to or from an AVL tree can cause the tree to become out of balance. So after adding or removing a node, the balance factor has to be checked in order to maintain the balance of the AVL tree. This is done by performing 3 steps. First, the insertion or removal of a node, then checking the balance factor of all ancestor nodes, and finally performing any rebalance operation if any of the nodes became out of balance. Let's take a look at the insertion of a new node. First, the new node is inserted. This is done just like in a regular binary search tree. Then the balance factor is checked for the parent and all ancestor nodes all the way up to the root. Now it's important that when the balance factor is checked, it is first computed on the parent, then checked. If any of these balance factors is out of the valid range, a rebalance operation is performed before checking any further ancestor nodes. There are 4 imbalance cases in an AVL tree. There's the left-left case, left-right case, right-left case, and the right-right case. You can see an example that's illustrated here. For the left-left case, there's a node that has a balance factor of 2. That tells you that this tree leans towards the left. Its left child node has a balance factor of 1, which also tells you this leans towards the left. So for the node with a balance factor of 1, the height of its left subtree is larger than the height of its right subtree. And the same applies for the node with a balance factor of 2. Its left subtree has a height that's larger than the height of its right subtree. Now for the second case, which is the left-right case, there's a node with a balance factor of 2 and its left child node has a balance factor of -1. So in this case, for the node with a balance factor of 2, the height of the left subtree is larger than the height of its right subtree. And for the node with a balance factor of -1, the height of the left subtree is smaller than the height of its right subtree. For the third case, which is the right-left case, there's a node with a balance factor of -2, and its right child node has a balance factor of 1. This tells you that the height of the left subtree for the node with a -2 balance factor is smaller than the height of its right subtree. And for the node with a balance factor of 1, the height of its left subtree is larger than the height of its right subtree. Finally, the fourth case is the right-right case. In this case, there's a node with a balance factor of -2, and its right child has a balance factor of -1. This leans towards the right. For the node with a balance factor of -2, the height of the left subtree will be smaller than the height of its right subtree, and the same applies to the node with a balance factor of -1. The height of its left subtree will be smaller than the height of its right subtree. Now for each of these cases, we have to perform a resolution. Resolutions are performed using rotations. For the left-left case, a single right rotation is performed. So we have this case, and the right rotation is performed around the node with a balance factor of 2. So 2 gets pulled down, while these two nodes get pushed up. The node with a balance factor of 1 will be in place where the 2 was. You can see it right here. For the left-right case, there's a double rotation. First, an inner left rotation, so this node gets pulled up to where the node with the balance factor of -1 was. -1 gets pulled down, and then we have a single line after the first inner left rotation. Now you may notice that this line matches the first case, the left-left case. So then we perform the same right rotation as we did already in the previous case. So 2 gets pulled down, these 2 nodes get pushed up, and this results in a full binary search tree. Now after these rotations, we have to recompute the balance factor. So the balance factor, if it's really just these nodes, would be 0 for each of these nodes. For the third case, which is the right-left case, a double rotation has to be performed as well. In this case, an inner right rotation, followed by an outer left rotation. The first rotation is performed around the node with a balance factor of 1. So 1 is pulled down, this node gets pushed up to where the 1 was. Then we have a single line, and then a left rotation around the node with a balance factor of -2 is performed. So 2 gets pulled down, these 2 nodes get pushed up. So again, we result in a perfectly balanced binary search tree. And the balance factor would have to be recomputed since these balance factors are no longer valid. The last case is the right-right case. In this case, we have a structure that looks similar like this, with a node with a balance factor of -2 and a node with a balance factor of -1. There's a single left rotation which matches the second rotation that we performed in the previous case here. We also had this line and we rotated around the root node of this tree or subtree. So here 2 gets pulled down, these 2 get pushed up, and then we will have a resulting full binary search tree. Now each of these cases are simplified. As I pointed out, there could be some subtrees on each of these nodes, but this gives you a full picture of the 4 different cases and how to resolve these cases. So again, there's a left-left case with a single rotation. The opposite would be the right-right case with a single left rotation. And then there's a left-right case and right-left case, which both have a double rotation. First an inner left rotation, followed by an outer right rotation, and the right-left case has an inner right rotation, followed by an outer left rotation. Now, this might sound overwhelming in the beginning, but with some practice, it's quite natural and you learn to remember it much better. So let's take a closer look at the left-left case. Here I have an AVL tree, 2 nodes, node 1 and node 2. Each of these have subtrees, so S1, S2 and S3. You can see that this tree already is hanging towards the left. Now inserting a new node under the S1 subtree will cause the balance factor of 2. So now that the tree is out of balance, and this is the left case. This is resolved by performing a right rotation around the node with a balance factor of 2. So N2 gets pushed up, N1 gets pulled down, and if you see the line here, this subtree is connected as the right subtree of N2. This 45-degree angle to the left now flips over to 45-degree to the right. So S2, the subtree S2, becomes the left subtree of N1. So this is what it looks like. Now N2 is at the top, at the root, N1 is the right child, and N1 has S2 as its left subtree. So this is where it was. N2 comes up, N1 gets down, and S2 is no longer the right subtree of N2, it's now the left subtree of N1. Let's take a look at the left-right case. So here again is an AVL tree. There are 3 nodes with some of these subtrees here. Now a new node is inserted underneath the S3 subtree. The balance factor is computed, and now it's out of balance. So this one would have a balance factor of 2, and this one would have a balance factor of -1. So it's a left-right case. So we have to perform 2 rotations. A left rotation around N2. So N2 gets pulled down, N3 gets pushed up, and the subtree S2, which was the left subtree of N3, becomes the right subtree of N2. So this is what it looks like after the first left rotation. So note that N2 gets pulled down and N3 gets pushed up. And S2 becomes now the right subtree of N2. Now the second rotation is around N1. So N1 gets pulled down, N3 gets pushed up. And then S3, which was the right subtree of N3, becomes the left subtree. This is what it looks like after. This is what it looked like before. Now I've shown the left case and the left-right case. The right-right and right-left imbalance cases are basically the exact opposite in terms of rotation. Let's see how we can build a new AVL tree. First I insert 5. This becomes the root node. It has a balance factor of 0, which is fine. Then I insert 10. 10 has now a balance factor of 0. Its parent has a balance factor of -1. This is still considered balanced. Now I insert 4. 4 is less than 5. This one has now a balance factor of 0. The parent has a balance factor of 0. This is a full binary search tree, so it's completely balanced. Then I insert 15. So again, this gets added as the right side of 10. And this is still considered balanced. It has a balance factor of -1. And the root has a balance factor of -1 as well, which is a valid balance factor. Now I insert 18. So 18 has a balance factor of 0, which is a leaf nodes. Leaf nodes always have a balance factor of 0. Its parent has a balance factor of -1, and its grandparent has a balance factor of -2. This one is invalid, so we have to perform a rotation. Which case are we looking at? You guessed it right, it's the right case. So we have to perform a single left rotation around node 10. So node 10 gets pulled down, and 15 with 18 gets pushed up. So the red one gets pulled down, orange one gets pulled up, single right rotation, and now we have 0, 0, 0 in terms of balance factor and -1 for the root. So now the AVL tree is balanced again. Now we insert 12. So 12 gets inserted as the right side of 10. The 10 has a balance factor of -1. 15 has a balance factor of 1. And the root node 5 has a balance factor of -2. Which case are we looking at? You guessed it right. This is the right-left case. So we have to perform 2 rotations. The first rotation is a right rotation around node 15. So 15 along with 18 get pulled down. So 15 will be where 18 was. 10 gets pushed up to the place where 15 is. And 12 is no longer the right child of 10. It now becomes the left child of 15, which will be here. So this is what it looks like after. If I go back, this is what it looks like before. So 15 and 18 get pulled down. You can see them here. If I go back, 10 gets pushed up to where 15 was. So we have 10 here, then 15, 18. So 10, 15, 18 in one line. 12 basically stays where it was, but from the left 45-degree angle, if you will, this flips over to 45 degrees towards the right and is now connected to the node 15. Now this was the first rotation. We still have to perform the second rotation, which is a left rotation around the root node. So the root node gets pulled down to where 4 is, 4 gets pulled down too, and 10 will become the new root node. So this is what it looks like. And after performing the second rotation, this tree is completely balanced again. So this is what it looked like before. 10 becomes the root node, and these two gets pulled down. Now we have a balanced tree. You can see when performing insert operations, the AVL tree always ensures that it remains balanced, and the same applies for removal operations. Let's take a look at the performance of the AVL tree. By computing the balance factor after insertion and deletion, the AVL tree ensures that it is always balanced. Rotations may trickle all the way up. So if it's a large AVL tree, there can be multiple rotations all the way up to the root. But each rotation has a runtime complexity of O1. That means it is constant. And the maximum number of rotations per insertion operations is the height divided by 2, so half the height. The insertion has a time complexity of O log 1, and even with the rotations, it's still an O log 1. So when we look at the performance of operations of insert, contains, and remove, we always maintain a log n performance. So this is much better than a regular binary search tree, which can result in the worst case into a linked list, and then we have ON. So in this, the AVL tree always ensures that we stay in logarithmic performance time. I hope you enjoyed this video. Thank you for watching.